That's good enough. Ah, I can hear it better now. Okay, yeah. Okay, oops. The chalk all got hidden. Probably Georg finished all the chalk. So, I've decided to change my third lecture. I'm sorry for those of you expecting homogenization. Because instead I thought I'd talk about a topic which relates both to what I've been talking about and also a little bit to what Mihail has been talking about. So, and this is the topic of biomixing. But it's really a more general topic than what it sounds like. But I'll tell you a little bit about what biomixing is. Biomixing is the idea that in some certain fluid environments, there are organisms in the fluid, such as fish in the ocean, but also in microenvironments and microfluidics, etc. You often have suspensions of bacteria, etc. And all of those organisms are moving around. And there are certain situations where they really are some substances that the bacteria want to consume or that the fish want to eat that are extremely diffusion limited, meaning they don't diffuse very fast. In this case, if you want to compute the degree of mixedness of the environment, you actually have to take into account the motion of the organisms themselves. In other words, the organisms stir the environment as they move around. And so a few years ago, the oceanographers got excited because there was a paper published which revived an actually older idea from the 60s that in order to compute oceanic transport quantities, you must take into account the motion of the fish. This turns out to be, I don't think many people believe that anymore. I think that it's probably true that in some places, in these massive swarms of dense krill or something like that, where there's trillions of organisms often, then there may be an impact. But except for a few diehard people, I don't think anybody actually believes that it has a role in, especially not in global motion mixing. I mean, the reason why it's not such a facetious idea, for those of you who are not oceanographers, which I am not, is that the ocean is funny, right? It's pretty easy to mix laterally, but it's extremely difficult to mix vertically in the ocean because the ocean is stratified. So the light stuff is on top and the heavy stuff is at the bottom. So the water parcels do not want to move up or down at all. So very complex processes are required to overturn the ocean. So internal waves coming from tides, for instance, are thought to be one of the main mechanisms. But people had the idea that in certain environments, there might be a biological contribution to the vertical mixing. Again, horizontally, there's no mixing problem in the ocean, but vertically, it's actually very difficult. And clearly, vertical mixing does happen because the organisms at the surface of the ocean need, sort of organic matter to reproduce, and non-organic matter like iron and phosphorus. And that stuff sinks, and yet somehow it gets back there. And we don't actually understand very well how all that stuff gets back there. It actually sinks in the form of something that has a beautiful name. It's called marine snow. Marine snow is the body's dead organisms that is sinking everywhere in the ocean slowly. But what happens is it never makes it to the bottom. It dissolves, right? And because of the action of bacteria, it never actually reaches the bottom. But the question is, how do all these things go back and eventually make it back to the surface of the ocean is a little bit of a mystery. So nevertheless, I got interested in this idea of trying to quantify how much mixing is done by swimming organisms. And it was suggested by some people that, yes, at first people looked at turbulence. So, if you have a big whale, it'll generate big eddies. And that's fine, but for small organisms, nobody really believes that turbulence is very important, right? If you're a small organism, you don't generate much of a turbulent wake. And so people brought back this classic idea of drift. There's two types of drift, two main types, which are actually really the same thing. The more well-known one is called Stokes drift, and it's the drift caused by a traveling wave. So if you're in the ocean, and a train of wave comes by, and you look at the motion of a particle, it actually bobs up and down, but actually does something a bit more subtle than that. It bobs up and down, but also has a net displacement. So particles under a wave bob up and down, but there is a small net motion, even though they mostly return to their initial position. And this is called Stokes drift. Okay, and it was shown, to exist by Stokes, so it's an old idea. But there's another type of drift, so this is Stokes drift, and it's very interesting, and again, there are many oceanographic calculations where you care about Stokes drift because it needs to let, waves in the ocean, they don't actually move stuff, right? It's just the water moving up and down. The wave itself doesn't actually displace fluid, except through Stokes drift, right? So there's a slow migration of particles as they're acted on by waves. But there's another type of drift, and it was first studied in terms of in inviscid fluid. So again, I'm not sure how many people here are fluid dynamicists, but inviscid means no viscosity. So it was first studied for things like an inviscid cylinder. So imagine that you have a cylindrical body moving through a fluid or a sphere, but let's think a two-dimensional cylinder. And let's imagine that you pick a reference particle, a fluid particle, and you solve the equation x dot, let me write r dot because that's what I'll use later in the notation. You solve the ordinary differential equation for the motion of fluid particles under the action of a velocity field. So this is the equation for ideal displacement of an idealized fluid particles, right? So my particle here have no mass. They're just fluid parcels. They're idealized mathematical points. So this moving body causes a drift. In fact, maybe it's better written like this. So we're actually evaluating it at some point r with respect to a moving body, where u is the velocity of the moving body and t is time. So in other words, r is the position of my particle, but I'm measuring its position compared to where a swimmer is at some time. Okay? And the swimmer is moving, so there's an explicit time dependence to the motion. And so then there are these motions that people have called elasticas. The motion of particles makes little ribbons like that. So the particle moves up because it wants to get out of the way of the swimming body, but then it moves back down, but it has a small net displacement. And I'm going to call that net displacement capital delta of r. It's a function of time, technically. For an inviscid fluid, what's interesting is that net displacement is actually finite. If I have a cylinder that starts from minus infinity and goes to plus infinity, there is a finite net displacement. So it's convergent. Partly because inviscid fluids are very, the effect of a moving body in a fluid without viscosity is very weak. There's no viscosity to conduct the motion, right? So you don't feel it very much. And so the displacement is convergent. If you take a sphere that is rigid and no slip, then the displacement is actually infinite if you wait long enough, because the viscous stresses are so well imparted. So there's some important names associated with this. So this is actually called Darwin drift or Darwinian drift, which is a funny name until you realize that this is Charles Darwin, whom you may have heard of, but it's actually Charles G. Darwin, who is the grandson of Charles Darwin and wrote a paper in 1959 on the drift due to a moving body, and so it has become known as Darwin drift. Yes. Yeah, so we both are at rest and we're watching this cylinder move from some large distance to some other large distance, and as it moves by, the fluid particle is displaced in time. No, sorry, this is a rigid, well, this is a body in the fluid, right? The thing that I've hashed is, so outside is the fluid, yes, that's right. So the cylinder you're going to think of as a fish, right? But right now I'm going to talk about cylinders. So Darwin, by the way, I was just reading a biography of Turing, and I guess Darwin was Turing's boss at the National Physics Laboratory in the UK, and supposedly a complete bastard. And Turing really hated him, and is one of the reasons why Turing left for Manchester. So they really had a big disagreement. So this is Charles G. Darwin, but in fact, even though everybody calls this Darwinian drift or Darwin drift, so Darwin is in 1959 or so, Maxwell wrote the exact same paper in 1869. So it should be called Maxwellian drift because Maxwell doesn't have enough things named after him. But then again, you might say the same thing about Darwin, so, except that this is not a Darwin, right? Lots of stuff is also named after Erasmus Darwin, Darwin's grandfather. So there's a nice kind of chain of Darwinism. This is a beautiful paper, by the way. Maxwell really plots these beautiful solutions, and it was very difficult in those days to plot. The exact solution of this involves elliptic functions, and you have to obtain those numerically. And the fact that in 1869 you would sit down and compute these things carefully. But Maxwell was a bit bitter about this. In his paper, he has some remark on, my pictures would look better if I had access to the tables of Professor Legendre. So somehow Legendre did not want to give him the data or something like that. That sentence makes it sound like there was a story there that I would like to know. Anyways, okay. So why is this relevant to biomixing? Well, because we're going to take the viewpoint that a fish moves in sort of like random paths. Okay? And as it moves in random paths, if you fix your eyes on one fluid particle, then every time the fish moves, this thing will move a bit, and then on this path, it would make another elastica. And then here, the fish would come pretty close, it would make another elastica. And here, it would get also close, make another elastica. So the particle, the random motion of the fish induces a random motion on the particle. And so our goal will be, first, there's a simple thing you can do, is to compute the effective diffusivity of the fluid particle given the properties of the random walk of the swimmer. But actually, we're going to do more. It turns out you can derive, to some, not quite analytically, in fact, in some cases, the probability density function for the displacements of the particle as a function of time. And the reason why you would want to do this is there are experiments that have measured these displacement functions for microswimmers, and I will show you that the theory that I'll present here matches the experiments to some remarkable degree of accuracy given these kinds of statistical theories. So that'll be the story. Probably it'll take me both lectures, this one and the next one, to show you all this. So this lecture, I'm not going to show you any plots, but next lecture, I'll bring my laptop again, and we'll show you some results. Okay? Questions so far before I embark upon the calculation? Okay. The swimmer is not going to do Brownian motion. So Brownian motion would be a natural, you could model the motion of the swimmer as Brownian motion. The problem with Brownian motion, first of all, is that nobody swims in Brownian motion, right? You really want a swimming motion which is much more correlated, right? Organisms tend to swim in relatively straight paths for a little while before perhaps deciding to change direction. You can solve this problem assuming Brownian motion for the fish, but then you don't even need to compute the displacement function, actually. It's a simpler problem in many ways. But today we'll assume that there's actually big paths, which is what brings in the drift function, right? You don't get one of these drift functions if your cylinder is just jiggling, right? I mean, there'll be some drift of the fluid particles around it, but it will not be this kind of sequence of beautiful paths of these, it will not be piecewise paths that are these elasticas. Okay? So I want some correlation to the motion because that's much more realistic as to how swimmers actually swim. Now, I will take something very simple where these swimmers will have fixed path lengths. And that's cheating, of course. That's not true. What you would want to do is you would want to give a distribution to these path lengths. But it turns out, and this is probably what makes the theory work so well, that the whole theory ends up being independent of the path lengths if they're long enough. And that's a bit of a surprise. It's not obvious that this should happen, which is great because it means that you don't really need to worry about the details of the path lengths, and that's why the experiments are matched so well by the theory. So it's a kind of accident of the way these things work out, which is very nice. Okay, great. So how am I going to model this? Well, first I have to solve this equation, and I'm going to take this as a given. So I'm going to take an object called delta of r and t, which is the drift, the displacement of a particle initially at r. Okay? Now this is for a single swimmer. So that's the theory is based on this idea in that you don't try to solve everything for a bunch of swimmers at once. you focus on understanding a single swimmer, and then you statistically arrange these swimmers together to understand what would happen if you had more of them. Okay? So this is assuming it's exactly the picture that I drew there, so I'm not going to redraw it. Delta is defined this way when you know exactly which direction the fish is moving, etc. Okay? And we're going to do the usual assumptions when you do this. We're going to assume homogeneity and isotropy of essentially everything. What does that mean? It means I'm in an infinite ocean, and there's no up or down or left or right. The fish are going to swim in every possible direction, and it's not going to depend where I start my fluid particle. The effective diffusivity will not depend on where I start my particle. Now, in fact, these assumptions can be relaxed, and it's actually an interesting thing that has not been done very much to relax these assumptions, especially, for instance, in the ocean, right? Because the ocean is stratified, you can definitely tell up from down. But we're going to assume that we're in a lake, not in the ocean. Lakes are also stratified, so we're going to assume that we're in, I don't know, there's not that many unstratified natural fluid bodies, but lakes are not very stratified, especially at certain times of the year. And also, the stratification of the ocean is actually quite weak and doesn't actually hinder swimming for most organisms. So the reason why I want to assume this is now I can assume that my swimmers are coming in from every direction. And let me write down the probability density for one swimmer. So here's what this means. There's a bit of an unfortunate notation here. So R is going to be the value of the displacement. Okay, so what is the probability of getting a displacement of size r after a time t? Well, I can write it as the following. I'm going to do an integral over my entire volume. Now, already, by the way, I'm cheating a little bit. I'm swindling you because I cannot possibly have homogeneity if I have a finite domain. But in the end, I'm going to take the limit of infinite domain. But I'm going to work as if everything was finite for the most part, and then eventually we'll take the limit. And as we'll see, there's a little bit of subtlety involved in taking that limit properly. Okay? So, the probability of getting a displacement of vectorial value r is going to be an integral of a delta function between the scalar r, so this is the magnitude of r, of r, minus the magnitude of the displacement. Okay? So I've already used isotropy in writing this because I only care, in other words, the probability of getting a certain displacement vectorially only depends on the magnitude of r, right? Because things are isotropic. There's a normalization factor here, which I'll write as 1 over alpha d r to the d plus 1, where alpha d is basically the solid angle value. So this is either going to be 2 pi or 4 pi, depending on whether you're in 2 dimensions or 3 dimensions, right? In higher dimensions, it's some gamma function of d over 2 or something like that. There's some way of computing the area of a d-dimensional sphere, right? So that's what this is, of the area of a d-dimensional unit sphere. Okay? So again, this is only the normalization, basically, so that things integrate to 1. Everybody clear on the notation here? The subscript 1 refers to one swimmer. Yes? It is d minus 1. Thank you very much. Yes, not much of an area if it's d plus 1. Thank you. Sure. So we want to compute the probability density of having a displacement, vectorial displacement r in some direction. Now, clearly, the probability of getting such a displacement should not depend on the angular direction of r because our system is isotropic. It has no preferred direction. And so it should only depend on the size of r. But if it's going to be having size of r, it is because the size of r coincides with some value of the displacement, delta, right? In other words, it has to be possible for the drift function to actually achieve the value r, and that's what the delta function is selecting for you. And the reason you're doing an integral is because there may be several values of delta corresponding to the same r, which would make it more likely that you're getting that value of the displacement. And you're integrating over all possible values of the displacement, and you're normalizing by the volume of the space. Okay? Is it clear? Great. So we can already compute some interesting quantities. So in fact, there's already an interesting result we can get from this, and it involves computing the second moment. Second moments of the displacement are a good friend of ours. So I'm going to write subscript 1 again to mean one organism. And I'm going to use the physicist notation of using angle brackets for averages rather than E, the expected value. I must admit, expected value is one of the worst names ever invented in the literature of mathematics, right? It's a terrible name. I mean, we have words like mean and average. Why introduce a new name? But also the expected value is often not realized, right? So why should it be expected? I don't think it's a very good name. So I don't understand why the probabilists insist on using that ugly, ugly word. Is mean so long to say? Or average? I don't know. By the way, I'm using a subscript here to tell you what variable constitutes the volume. Okay, so the expected value of the squared displacement should be this integral, right? The average squared displacement. But then if I insert my delta function and exploit the, whatever delta functions are designed for, which is to remove an integral, I get this nice result. And there's still an over V. Okay. So this is nice, but it doesn't tell us, well, this would tell us a value about the mean displacement of a particle due to one swimmer, but if I take the infinite volume limit, I would expect to get 0, right? Because I have an infinite volume, I only have one swimmer, so on average my swimmer is going to be nowhere near me, and so nothing's going to happen. Again, you could cook up some crazy divergent displacement functions if you wanted to, but a typical displacement function will decay nicely far away, and because you take the infinite volume limit, you're going to, actually, the integral could even blow up, right, as long as it doesn't blow up faster than V, and this would still go to 0. So, in all likelihood, this goes to 0, so this is not the right thing to look at, in some sense, in the infinite volume limit. Sorry? I only use the subscript eta because sometimes I'm integrating over r and sometimes I'm integrating over eta, right? So, sorry, what is what? Eta? dv eta, yes. Think of it as d eta x, d eta y, d eta z. It's just a vector, it's an integration variable. Okay, so how do I scale this up to many swimmers? Well, this is where another modeling assumption occurs, is that we're going to assume that the swimmers are completely independent of each other. And in fact, not only are they independent, their swimming is not affected by each other, but the effect on the particle is also independent of each other. So this is a dilute limit. It's saying that there's few enough swimmers that the likelihood of having two swimmers near my particle at any given time is negligible. So it's neglecting correlations between swimmers. Again, I'm thinking a little bit about possible project ideas here. An interesting thing is to try to relax that assumption, but that's actually very difficult to try to put in some correlations. But probably it could be done weakly, consider two swimmer modifications. So, assuming that the swimmers are independent, then there's a very nice property of the variance, is that, by the way, this is the variance because also quite clearly the average of R itself is 0, right? Because of isotropy, right? So on average, my particle goes nowhere because the system is isotropic. So it's going to be displaced, but on average, it's going to not go anywhere. So now if I think of the n swimmer quantity, right? So if I have n, capital N swimmers, because they're completely independent, that's actually just going to be capital N times the value for one swimmer. But now look at this nice trick. Let me define little n to be n over v, the number density. Right? The number of swimmers per unit volume. Now look at the nice thing that happens. If I multiply this expression by n, I can now pull out the v from inside the integral, and I get that this is n, the integral over the volume, delta squared dv. And so now there's actually a question of whether the integral here is convergent or not, right? This integral. So that depends on the specific model of the swimmer you're talking about. But in fact, for many, many types of swimmers, this integral is not only convergent, but it does something beautiful. It's linear in time, which is exactly what you need for this to be a diffusive process. So this is linear in time, which is exactly why I don't need to worry about whether my swimmers change direction or not. In this ensemble average sense, it doesn't actually matter. The path length doesn't actually matter because this integral tends to be linear in time. Not always, but in some typical cases. Why should it be linear in... The question is, why should it be linear in time? Okay? And this is where maybe a little bit of physical intuition helps. What is this integral? Right? It's the integral of the squared displacement for one swimmer. Okay? So what is the history of a typical fluid particle? So my swimmer moves here, and a fluid particle typically feels the swimmer and then gets left behind, but it typically moves a finite distance. Okay? That's important. Meaning, the reason why they move a finite distance is that they're kind of left behind by the swimmer, right? So you might ask, well, what does that say about this integral? Well, it means the value of delta is, roughly speaking, capped at some maximum, right, corresponding to the maximum displacement. However, the support of this integral grows because the longer you wait, the more particles your swimmer meets. And that's exactly why this grows linearly in time. You're carving out a cylinder of length u times t, and in this cylinder, you displace these particles by a finite amount. But it's the number of displaced particles that grows linearly in time. Okay? So in other words, this typically does go actually as, in this case, let's write it as 2d diffusion constant time. So this is the dimension defined before, and this is the effective diffusivity. No. The swimmer is the cylinder. The swimmer is the disk that I'm drawing. Yeah. All in red. Yes, that's right. Yeah. No. The cylinder is the swimmer. Right? Yeah, N cylinders, yes. Or swimmers, exactly. Yes, they're all over the place. But we fix, right now we're really thinking of one particle, and we're seeing the effect of the N swimmers on that one particle. But because of homogeneity, all these particles are going to be independent, right? And we can, if we compute the effective diffusivity for one particle, then we'll find the effective diffusivity for the whole medium. Again, this is a modeling assumption in the sense that, of course, if you start two particles near each other, they're going to be correlated for quite a while, but eventually they'll decorrelate, and then they'll evolve independently. Very clear? Again, the particles are outside the cylinder, right? Okay. Oh, but that's the assumption I just mentioned. We're assuming that the fluid is so dilute that you never meet two cylinders at once, right? If I do meet two cylinders, it'll be one after the other, right? It's a correction to consider the case where two cylinders happen to be near a fluid particle at the same time. At higher densities, it'll be a very important correction, but in the limit of very low densities, it's essentially a negligible event. That's the same assumption that's done in gas dynamics and all sorts of things, right? It's a very standard. Neglecting higher order correlation is a very standard assumption. Absolutely. Yes? Sorry, can you speak loudly? Yeah. What is the particle? What is the particle? As I said, it's a mathematical idealized fluid particle, right? So it's just a mathematical point in the fluid that is my particle. Is that your question? You could imagine it to be a small particle, but yeah. It could be that what could be different? So why? I don't understand why that is. It's an idealized fluid particle, right? I'm assuming that it's moving with the fluid. So are you saying in practice it could be different? Sorry, you're not speaking very loud. I guess I don't understand your question. Active in what sense? But that doesn't, none of this is important here, right? Why would there be a difference between an active swimmer and a passive swimmer? There really isn't. My drift function here can actually include a time dependence, right? My sphere might have some internal degrees of freedom, and that would just be embodied in delta. It would be embodied in the way I've solved that for that displacement function, right? Okay, if the swimmer does something which is not statistically steady, right? If it does one behavior at one time and another type of behavior later, then there's not much I can do about that. But if it's doing something relatively steady and consistent, then I can build that all into my drift function. In other words, I just have to measure how far typical particles drift as the swimmer comes by for every possible value of points around the fish. And that whole function, in some sense, embodies the behavior of the fish. As long as that behavior is relatively steady and consistent, then that function captures everything. That's kind of an advantage of this model, right, is that you don't have to overthink how you're going to model the swim. You can really break down the problem into two parts. The statistical aspect of understanding how you combine the swimmers, and then you focus on the specific problem of your particular swimmer. Yeah. Okay? Sure. So imagine that particle, so my sphere is moving in a tube, right? And particles in that tube, I mean, my tube is actually bigger, it doesn't matter, but let's draw it at the size of each fluid particle in this gets displaced by some finite amount. That amount could actually be different for different fluid particles, it depends on how far you are from the swimming axis in a way, right? But the important thing is that it's finite. And so you see the swimmer, that my chalk is the particle and my hand is the swimmer, my fist. I see the swimmer, I get displaced, and then I stop because the swimmer has passed me and I no longer really feel it. So the value of delta itself is finite for any fluid particle. But since I'm integrating over time, the longer I wait, the more fluid particles I've encountered. And so the length of my cylinder is growing linearly in time. So the value of the integral will tend to grow linearly in time. Okay? So in other words, it's almost as if delta were a constant value over the cylinder, but because the cylinder is getting longer and longer in time, it means the value of this integral is growing linearly in time. Okay? Yeah. Yeah, so you're saying if it starts to curve. Yeah. So this is, again, where we're saved a little bit by this fact that this integral is linear, right? You're perfectly right. If I put some little curvature here, right, things will change, but they won't really change that much. It's still going to be the volume of that tube that will matter, and the length of that tube, even if the tube is like this, right, is still growing linearly in time. Now, if it starts to wiggle, if the fish were really changing direction rapidly, then this would break down. But this is why I'm not modeling it like something like Brownian motion. So this only works for fish that are relatively, determined to move forward a little bit before suddenly deciding to change direction. It's not for fish that are kind of like oscillating a lot. That's right. No. That's exactly the point. The particle only moves when it's near the swimmer, right? But the particle moves by a finite distance. So the distance by which a particle has moved is not a function of time in some sense, right? Because once the fish has passed it, it's reached a maximum value. So the value of delta itself for a given particle is some fixed value. But the number of particles the fish encounters is growing in time. Yeah. So the linearity is not due to the linearity of the drift function itself. It's due to the fact that the support of the integral is growing linearly in time. Okay? Again, this is a very standard viewpoint if you do statistical physics, right? That's exactly how you compute cross-sections of probabilities of, interactions of collisions between particles, right? As you draw little tubes around the particles, and that's the volume in which an interaction could have happened. That's exactly the same thing. But here it leads us to conclude immediately that there's going to be a kind of random walk diffusive behavior, and this is a perfectly computable number. In fact, probably in the next lecture, I will show you a model where you can compute this exactly. Okay? In fact, this is simple enough that there are several models where you can actually compute this number explicitly. And then the question will be whether we can match this to any kind of experiment. Okay? How am I doing on time? I'm doing pretty well. Okay. So, what I want to compute is actually a bit more than that. The squared displacement, the expected value of the squared displacement is actually a wonderful thing to compute, and lots of people are very happy, to be able to compute this. But you can use this framework to also compute the entire, you can compute Pn of R. So this is P1 of R, and I computed the nth n-swimmer variance by combining my single swimmer variance. But now I'd like to show you how to combine my P1s to make a Pn, right? A probability density function for the displacements for n swimmers. Okay? Again, it has the advantage, this is a nice calculation because you can do a lot of things explicitly. And in fact, I'll show you a simple example where you can actually carry the calculation the whole way. It will also surprisingly provide a nice example for the kind of things that Mihail has been talking about when dealing with Poisson processes. At least I think a nice example for that. Okay. So let me first find something else than P1. I don't actually want the P1 of the whole displacement. Let me find instead the probability density function for one coordinate. In other words, P1 is the probability of having any value of the vector displacement, but I'm going to project along one axis, and because it's isotropic, I can pick any axis that I want, right? So I'll pick the x-axis. Okay? And so this is the marginal distribution over the other variable. So let me do the two-dimensional case. Right? So I would want to integrate, I would want to find the marginal distribution over the other variable, and then I can insert my formula for P1 of R from over there, interchange the order of differentiation, assuming that things converge nicely, and I get the following. I'm in two dimensions, so I'm going to use 2 pi r delta of R minus delta Again, that's just using the specific value d equals 2 in my formula over there. Let me just write that down. D equals 2. But then, of course, you can exploit the delta function to be able to carry out an integral. And remember that r squared here is going to be x squared plus y squared. So if I want to use the value of the delta function, I have to solve for when r is equal to delta, so when y is equal to delta. And I want to evaluate, sorry, there's a dy. There's a dy first here, right? Sorry, I missed a dy inside of the integral. But when you use a delta function, you have to also use the derivative of the function, right, as a weight. So there's a Jacobian, in other words, when evaluating a delta function of a function. And so when you evaluate this, you get the following formula. And then I'm introducing some notation here that I'll tell you about in a second. So here, I use the notation that bracket A is the indicator function for the condition A. So in other words, this is equal to 1 if A is true and 0 otherwise. Okay. So again, there's a little bit of, this is the Jacobian from exploiting the delta function, but then you also have to keep in mind that the only way you can get a displacement whose value is x is if the original displacement was bigger than x, and then it can project down to some value x, right? In other words, if a displacement at a certain point is less than the value that you're asking for, it's impossible that you'll get it, even after angular averaging. But if the displacement is bigger than your displacement that you're asking for, then it might be delta has a projection onto x, right? And the weight of that projection is this, meaning the likelihood of getting such a projection in 2 dimensions is exactly this Jacobian. Okay? In 3 dimensions, this is a different factor, so that you have to do the calculation separately. Right. So I'm not going to write down the 3-dimensional version. Well, let me just write that in 3 dimensions. How much time do I have? Yeah, 3D P1 of xt is a very similar integral, but the weight is actually just 1 over delta. And then the same indicator function. So the only thing that changes in 3D is the weight is this rather than this. So the weight is actually independent of x. Okay, questions so far? So now we have a marginal distribution of our p. So that's a nicer object to work with a little bit because because of isotropy, really, if we can find the information about one coordinate, we know everything, right? So there's really no point in finding p1 of r vector as we had before. Okay, so this is going to turn out to be a bit simpler. Okay, so I mean we can't evaluate this integral, right? Because we don't know delta. But now let's ask what we want to do with P1. So P1 again is the probability of displacement along the x direction due to 1 swimmer, and I would like to know the probability distribution for n swimmers. So I need to combine my P1s together, given that x is an additive variable, right? Given that I'm going to look for sums of swimmers. And so I'm not sure this has been covered in your lectures, probably, maybe it has. When you have additive variables, the way to do this is to find the characteristic function, right? So in other words, if I have x plus y, if x and y are random variables and I consider x plus y, then the probability density is given by the convolution of the 2 distributions. But convolutions are nasty things to compute in real space, but in Fourier space, they're wonderful because they just become a power. So you just multiply the characteristic functions together. And that's how you get things like the central limit theorem and all sorts of goodness. So let's find the characteristic function of our P1. Okay, so the characteristic function is the following. It's the expected value of e to the I kx, again for one swimmer, and it's going by integral minus infinity to infinity, P1 of the coordinate x and t, e to the I kx dx. Okay. Actually, here I do it for 3D, so let me do the 3D calculation. So this is going to be 1/2 the integral over v, 1 over delta a to the t, integral minus infinity to infinity of my characteristic function, sorry, my indicator function, e to the I kx dx dv over v. Okay. So the role of the characteristic the role of the indicator function, there's some terminology issues, right? Because characteristic function is often used to mean the indicator function in some communities. So I keep having to flip back. So this is the indicator function, and this is the characteristic function. But this condition here just says that x has to be less than delta. So this is just windowing our integral, right? So now I can carry out this integral, no problem, and I get that this is going to be the integral over v of the sinc. I'll tell you what sinc is if you don't know this function. dv eta over v, where sinc of x is sine x over x and 1. Right? It's the regularized sine x over x. Right? Engineers like to use the sinc function, signal processing people. In fact, you have to be very careful with sinc. I mean, you don't have to use it, right? You can leave it as sine x over x if you want. It's just that in this case, since I'll be using this function a lot, it's nice to use it. And then I was doing this calculation on MATLAB, and I was getting the wrong answer for like a whole morning. And then you figure out that your wrong answer is off by a factor of 3.14. So you go, And eventually you figure out that MATLAB defines sinc as sine of pi x over pi x. Yeah, so be careful. Goddamn MATLAB, I lost a morning because of you. And so that's the characteristic function for 3 dimensions. So that's for d equals 3. And the d equals 2 answer is actually, well, maybe I'll write it. For d equals 2, the characteristic function turns out to involve a Bessel function. Okay? Great. 10 minutes, all right. Okay, and let me box that up as well. So now that I have my characteristic functions, I want to combine them in order to get the characteristic function for n swimmers. Okay, but that's easy now, right? So I just say that, oh no, let me just do one thing. So these are actually not quite in the form that I want them. There's a subtlety about the infinite volume. Ask yourself, what will happen if I take the limit of v goes to infinity? So I think we can all accept that delta should go to 0 at infinity, right? The drift due to a swimmer should be 0 if you're very far away from the swimmer. So, in other words, most of the time over this integral, this function's argument will be 0. Well, what's sinc of 0? 1. And what's j0 of 0? It's 1. So these integrals in the form that are written are going to diverge wildly as I take to infinity. Okay? So this looks like a disaster, but it's only because exactly. So the whole thing will go to 1. Sorry. Yeah, that's right. Yeah, that's right. But I'm going to have n swimmers, so that'll go to infinity when I take the number of swimmers to infinity. Yes. So something will go to infinity. Okay? What? So here's what, but I'm going to exploit exactly what you've said. I'm going to add and subtract 1 in a clever way. So I'm going to write this as integral of dv over v. Let's see. Plus the integral of sinc of k delta minus 1 dv over v. And I think we can all agree that this is still correct because this is 1, right? So this is equal to 1. And then this behaves correctly, right? Because sinc of 0 is 0, but that'll cancel out this 1. So this integral will be convergent nicely as I take the limit as v goes to infinity. So it's the same thing that you said, it goes to 1, but it'll turn out to be that this is the right way of writing it. Okay? And in fact, I'm going to define this to be 1 minus gamma of kt divided by v, where gamma of kt is the integral of little gamma of k delta dv, and little gamma of k delta is either 1 minus sinc or 1 minus j0 gamma of x. So d equals 3 and d equals 2. Okay? Let me make sure that I wrote everything down properly. I think this looks good. Okay. Questions so far? So now maybe I have time just to wrap up the results for the convolution. So the characteristic function now for n swimmers will be the nth power of the characteristic function for 1 swimmer. Okay, that's elementary probability theory, and is really at the heart of, again, things like the central limit theorem, right? That's really how you prove the central limit theorem, and it's an incredibly useful thing. And so if you look at my expression over there, this is 1 minus gamma over v to the nth power. Okay? So now I want to take 2 limits, right? I want to take the thermodynamic limit, as it's often called. I want to take a large volume, but I also want to take a lot of swimmers so that the density remains constant. Okay, so I want to take both n and v to infinity. So remember that the number density is n over v. This exponent is actually just nv. Right? And I would like to take v to infinity, holding little n constant. And so you can see that this is going to be an exponential. Minus little n gamma of kt as v goes to infinity and constant. Okay? Now, there is a subtlety here that I'm not going to get into, that you have to make sure that gamma behaves in the right way as you take v goes to infinity, Okay? It turns out that gamma is even allowed to diverge as long as gamma is of order v to half, little o v to the half, then you're actually okay. Okay? It's actually an interesting question, and this is another thing that could be a nice little project problem, is to get a gamma which violates this condition. Then you can still take this limit, but you have one more term in the exponential here, like a quadratic term in n, basically. So you get a more interesting dependence, the number density. Okay? So I don't know if that's actually interesting, and I don't know if there's any swimming organisms for which this would actually happen, but I think it would still be interesting to explore conditions under which this happens. I should point out, though, that in practice, of course, for the swimmers I'm going to talk about here, it's much better than that. Gamma is actually a convergent integral as v goes to infinity, because the influence of the swimmer decays fast enough that the integral converges. So it's all about how far the influence of the swimmer occurs. The worst case scenario, right, the worst case is gamma going as O of v, because that means that my drift function somehow doesn't decay, right, which is about the worst you can expect. I mean, you could imagine the drift function grows, right, but it's hard to see what kind of swimmer would have an effect where at infinity things get more and more displaced by the swimming organism. Actually, that's not completely ridiculous, but if you have boundaries and you have a swimmer, there could be a backflow, right? But then you don't have homogeneity either, so it isn't necessarily realistic. And so now we're actually kind of done with this first part. We can write down the probability distribution for n swimmers in closed form. Well, sorry, in integral form. So what we say is the thing that we're after, the Pn of xt, is the inverse Fourier transform of my characteristic function right? And so that is 1 over 2 pi integral minus infinity to infinity of e to the minus n gamma kt e to the minus I dk. So, as you can see, the key here is twofold, right? First, you give me, if you want to carry out this modeling for a certain system, first you find the function capital delta, the drift function, due to one swimmer. Then you compute the function that appears in the exponent here, gamma, by integrating your drift function, composed with this function little gamma for every k. And finally, you take the inverse Fourier transform of the result, and that gives you your answer, your distribution. And then you try to compare to experiments somehow if you can. So in the next lecture, what I'm going to do is first I'm going to show you a little model, which is very nice because you can actually do all this analytically, which is rather surprising. And it's not an unrealistic model of some type of swimming organism, as I'll get into detail, as I'll mention. So it's actually rather remarkable that there exists any model you could solve analytically in this case, but there is at least one that I know of. And then I will tell you about a drift function for a much more realistic swimmer, and then you have to do things numerically, but you can still say some things analytically. And we'll use that drift function to compare to some real experiments of these displacement by swimming organisms, and we'll see how well we do. So, thank you.